All right, let's talk about chapter 3, and we need to consider the mole as well as molar mass. All right, let's make sure we got a brief review here of elements and compounds. We have atomic elements. These are the elements whose particles are single atoms, and these would be considered to be like the noble gases, and we'd see neon. We also look at the metals frequently this way, and those would be things like sodium, even if they are multiple actual particles in real life. Molecular elements are those that exist as multi-atom molecules in that they're neutral and they're going to be made here mostly of nonmetals, and we're looking at things like oxygen or sulfur held together by covalent bonds, and they're multi-atom molecules. Now, molecular compounds are going to be compounds whose molecules are made entirely of nonmetals. Again, these are going to be neutral, and these are things like carbon dioxide or water. And then we have ionic compounds. And ionic compounds are those made up of cations or metals, and anions, those are things like NaCl. And the difference when we write these is that NaCl is actually a massive three-dimensional compound such that the ratio of sodium to chlorine is 1:1. But when we say H2O, we really mean 2 atoms of hydrogen and 1 atom of oxygen, and the molecule stops right there. There's a few that you need to remember, and you need to remember the diatomics. And so if you hear hydrogen, if we're balancing an equation and they say something reacts with hydrogen, we need to realize it's H2, and nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all exist as diatomic. So these are your diatomic elements, and you need to put those and commit those to memory. All right, we left off on chapter 2 talking about masses of our elements. And for example, if we go onto our periodic table and we look up carbon, we will see that the average atomic mass, looking at the isotopes of carbon, is 12.01. It's going to be 12.01 units of AMUs per atom. And if we want to know what the mass of one molecule of, for example, here, chloroform, CHCl3, we realize it's made up of 1 carbon, 1 hydrogen, and 3 chlorines. And we're going to go to the periodic table. We're going to find the average atomic mass in AMUs per atom and multiply by the quantity at which we have and add them up. And we will get the mass of the molecule, and we would have this mass here in AMUs per molecule. Now we can do this for any molecule, no matter how complicated it is. So for example, if we're looking at this molecule, which is quite complicated, such that we have 13 carbons, 18 hydrogens, and 2 oxygens, take the number of atoms that we have, multiply by the average atomic mass off the periodic table, add up the values, and we will get the mass of this molecule in AMUs per molecule. Realizing again, in this molecule, we know we have 13 atoms of carbon, 18 atoms of hydrogen, and 2 atoms of oxygen. Now, ionic compounds are a little different. Ionic compounds, because it's a series of plus and minus charges, and we know opposites attract, it doesn't just stop at Na plus and Cl minus. It can keep going because this negative can attract that positive, and we can put more down here, and this becomes a massive three-dimensional compound. But the key is that the ratio is 1:1. So when we want the formula mass, we don't call it molecular because it's not a molecule. We call it formula mass of this ionic compound. It would just be our ratio, 1 sodium, 1 chlorine, multiplied by their masses off of the periodic table, giving us the total formula mass, or the mass of this formula unit. The formula unit here is going to be the 1:1 ratio, and its mass is 58.44 grams per mole. Excuse me, 58.44 AMUs per atom. All right, so we have these AMUs and we have atoms, but we have a problem, and we know that atoms are tiny. 1 AMU is equal to 1.6605 times 10 to the minus 24 grams. All right, that is unweighable in anything that we have in the lab, and we can't find atoms because they're so tiny. So we've got to figure out how we're going to take and look at our molecules, and we know that our molecules exist in ratios, discrete ratios of atoms. So we've got to figure out how we can figure out how much hydrogen we need to make some water, we knowing that our ratio is 2 atoms of hydrogen to 1 atom of oxygen if atoms are too small to find or weigh, giving us a serious issue. So here's what we're going to do. We're going to do counting by weighing. Counting by weighing is simply a way to realize if we know how much one thing weighs, then if we have 10 times as much weight, we have 10 times as many as that thing is. And to do this, we're going to define a term called a mole. 1 mole is exactly the number of atoms in 12 grams of the isotope carbon-12. This works out to be this number. We tend to cut this off at 6.022, and at 6.022 times 10 to the 23rd. Now note, a mole is a number, like a dozen. It's the word version of a number. So if we say 1 mole, it's the same as this number, just the way a dozen is the same as 12, or a pair is the same as 2. Now we have another name for this. We not only call it a mole, we call it n sub a, and we call it Avogadro's number. And it is 6.022 times 10 to the 23rd. That's how many we have of anything in 1 mole. Now, this is really useful because if we look up here at how much 1 AMU is, or for example, how much 1 hydrogen atom weighs, if we think about multiplying this value here multiplied by the number of grams per AMU, we notice those kind of cancel each other out, and that's going to give us units of about grams, which is going to be really useful. So 6.022 times 10 to the 23rd atoms is 1 mole. Now, on the periodic table, let's just deal with this for just a second. So I'm going to, for the sake of argument, find magnesium. Magnesium here, if we look at the periodic table, weighs 24.31, taking 4 sig figs off the periodic table. We know that has units of AMUs per atom. Now, AMUs per atom doesn't do us any good whatsoever because AMU is too light and atoms are too small to find. But we know a few things. We know that there's 1.6605 times 10 to the minus 24 grams per AMU. Please don't memorize that. And we know that there are 6.022 times 10 to the 23rd anything per mole. And in this case, our anything is atoms. Why would we want to do that? Well, when we do that, we are going to realize that if we take these two numbers and multiply them, they work out to be exactly 1. What use is that to us? It tells you that the amount of AMUs per atom, or an average atom, is the same as the number of grams per mole for anything. AMUs per atom is exactly equal to grams per mole. Why does that help? Because we know if we weigh out a certain number of grams, we actually know how many of something we have. So for example, if we weigh out 63.5 grams of copper, we will have 1 mole of copper. If we weigh out 12.0 grams of carbon, we will have 1 mole of carbon. And our compounds can either, or elements can either react in terms of 1-to-1 of atoms or 1-to-1 in terms of moles. It's just a ratio. So if we have that our 1 mole of carbon atoms is 12.0 grams and 1 carbon atom is 12.0 AMUs, then again here our grams and our AMUs are going to work out so that if we take a look at the atomic mass of something, it is going to exactly equal the molar mass in terms of grams per mole. So into your head stick that the molar mass is always going to have units of grams per mole. And we're going to have to use this because in our lab we can only weigh grams. So how does this help? Well, we realize then that the mass of a molecule in AMUs per atom, or AMUs per molecule, is going to be exactly the same as the mass in grams per mole. So everything we figured out before is completely usable now. The mass of water here would be 2 atoms of hydrogen times 1.0 AMUs per atom, 1 atom of oxygen multiplied by 16.0 AMUs per atom, giving us 18.02 AMUs per molecule, and that is exactly the same as the number of grams per mole. So we're simply going to take AMUs per molecule, and after chapter 2, completely ignore it and work entirely in grams per mole. So if we take a look at this molecule here, where we have 2 carbons and we have 5 hydrogens and 2 oxygens and 1 nitrogen, we are simply going to take the number of moles that we have, which would be 2 moles of carbon, multiplied by its mass, 12.01 grams per mole, and that's going to give us the mass of carbon. Units are now grams, and we could continue to do this with 5 moles of hydrogen, keeping track of the fact that this is a mole now, and 1.008 grams per mole. Now, how many sig figs you need in your question or molar mass depends on how many they give you in the question. So if they say that you have, you want the molar mass to 3 sig figs, or they give you that you have 12.5 grams of something and you want moles, realize that 12.5 grams is 3 sig figs, so you need your molar mass to 3 sig figs. So continuing, we would take and we would multiply this through, and we would add all of these up and get the molar mass in units of grams per mole.